Optimization problems. Essential question: how do I use derivatives to maximize or minimize some aspect of a situation? Let's take a look at this problem where 2,400 feet of fencing are used to fence off a rectangular field bounded by a river. Only 3 sides are needed for the rectangle. If we set up some dimensions, 100 by 2,200, which will add up to 2,400, we find that we get surround this amount of area. If we change the dimensions, we get this amount of area. And if we change them again, we get this. So somewhere there is some dimensions that will maximize the area. Let's go ahead and use variables to put that up. And we should always start with trying to write down what we're trying to optimize. We want to find the maximum area. Well, actually, we want to find the dimensions of the largest area, but we'll just say that. So let's go ahead and write our area function. Our area function is x times y. We also have some information about perimeter. 2,400 is equal to 2x plus y. We're going to use this to help us get area in terms of one variable, 2,400 minus 2x. So instead of y, I'm going to substitute this portion right here. And so our area is going to be 2,400x if I distribute minus 2x squared. So I fulfilled writing down my function. Now my domain, what is x going to be? X is going to be between 0 and remember, if only these 2 sides are being used for fencing, that's 1,200. Now this will probably not be used because these don't create a rectangle, don't create area. All right, so now we're going to use Fermat's theorem and go ahead and find the derivative. That's where critical information is found and the critical points are found. We're going to set the first derivative equal to 0, and when that happens, we set this equal to 0, and we can see our critical point is going to be 600. Now, to find out whether this is max or min, we're going to take the second derivative, and that's going to be -4. Now, I'm not surprised by these results because this is a parabola that's facing down. So for me to get a maximum, this is concave down, this makes a lot of sense. So by the second derivative test, a prime of 600 equals 0, and a double prime of 600 is negative. That implies a maximum. Now it says what are the dimensions, and so the dimensions, always try to answer the question. The dimensions will be 600 by, and if I go ahead and put, remember that I'm trying to find over here, if I write 600, 1,200 there, then it'll be 1,200 for y. And I should be putting units here, feet, and then this will be feet as well. Okay, we want to find the point on the parabola that is closest to the point 1, 4. So we want to find the minimum distance. Now the distance formula is going to be root, and it's going to be x minus 1 quantity squared plus y minus 4 quantity squared. To make life easier, we're going to minimize actually the square of this. So if we can minimize what's under the square root, we'll minimize the square root of that number. And I also know this relationship, y squared is equal to 2x. So x is equal to y squared over 2. So instead of x, I am going to write this. So everything will be in terms of y. So d is equal to, and we have y squared over 2 minus 1 quantity squared plus y minus 4 quantity squared. I'm going to use Fermat's method, find the derivative. I'll go ahead and just use the chain rule, and then the derivative of this inside function will be y plus 2 times y minus 4. Now that will simplify to y cubed minus 8. So I'm going to set the derivative equal to 0, and I'm going to get 0 is equal to y cubed minus 8, and my critical point will be 2. Now I'm going to use the second derivative test like I did on the previous one. I'm going to find the second derivative, and that's going to be 3y squared. So the second derivative at 2 is positive, and that implies that I am going to be concave up, which means that this point is a local min. Alright, well I don't really have a closed interval here, so that's going to be the minimum I'm looking for. Again, by the second derivative test, d prime of 2 is equal to 0, d double prime of 2 is positive, which implies a minimum. Now, I want to answer the question which says find that point, and I have found the y, which is 2, and now to find the x, I'm going to use this up here, so I'm going to write 2 squared is equal to 2 times x, and I can see x is equal to 2. So this is the point I'm looking for. This is the point on the curve that is closest to 1, 4. And here's the answer again. Okay, a man launches his boat from point A, and he can row and he can run. And we want to know where does he land so that he can minimize the amount of time that he's going to use to get to point B. So let's go ahead and write out what we want. We want to find the minimum time, and the time altogether is the time he rows plus the time he runs. And remember, distance equals rate times time, and distance over rate is equal to time. So we're going to call this distance from here to here, we're going to call that x. So this is his distance to row right here. So that's going to be the square root of 3 squared plus x squared. I'm using the Pythagorean theorem because this length is 3 and this is x. So that's the distance, and now I'm going to divide by his rate, and his rate is 6. Now the amount he runs, so once he lands, this is how much he's going to run, so that's going to be 8 minus x, and he runs at 8 kilometers per hour. So this is our formula. That's probably the hardest part of this problem, is to get that formula. Alright, now once we get the formula, we also need to consider the interval. And the interval is x can be 0, so he can go straight to the shore and then run the rest of the way. Or the other thing is that x can be actually 8. And that would mean if x is actually 8 that he rows all the way. So this is a closed interval that we need to investigate. Alright, let's take a look at how we go about doing it. Here is the equation, and I went ahead and found the derivative and I simplified it. Set it equal to 0, and put the negative 1/8 to the other side, cross multiplied, and then I ended up solving for x, and x was 9 over root 7. So I used the first derivative test because I really didn't want to take a second derivative, and I know at 9 over root 7 it's 0, and I tested a point before and a point after, and you can do that easily with your calculator. You can see I put it into y sub 1, I put the derivative in y sub 2, and I can go ahead and actually find the values. So I'm going to want to find the value y sub 2, and I'm going to want to find the y sub 2 at 0. And you can see it's a negative like it's shown. And then I'm going to do it up again. And this time I'm going to evaluate it at 4. And I'm going to enter, and you can see it's a positive value. So that's how I got these negative and positive values. So I know this is a local min, but before I can actually say it's the absolute min, I have to go ahead and evaluate on the closed interval that I was talking about before. And when you actually put these in, and you can go ahead and use your calculator again. And remember, in y equals, this is the function y sub 1. So I can go ahead and evaluate at y sub 1. And I can evaluate at my first point, which is at 0. And I get 1.5. So this value right here is 1.5. And if I put this in the calculator, it'll be approximately, after I round, 1.33. And when I evaluate here, this will be approximately 1.42. So by the closed interval test, this will be the absolute min.